set it to record to my computer this time. And now I'm going to pin the notes here. So these are now what you should see in case anybody needs to go through that. All right, so we're here. Everyone's mostly ready to go. So a couple of quick questions and then a couple of announcements. So just any feedback on the labs. It sounds like they're going okay. There's a little bit of rockiness in the start, but we're getting through that, right? So one question I had, there was only like 4 or 5 of you at the Wednesday session, but I did not see the Friday session. I think there was like a giant lopsidedness of attendance in the Friday. Like how many people were there this morning? Can someone who was there answer that for me?
I think I saw around 9.
Oh, no. But I think we're a bit skewed towards the Friday lab, which is not ideal. So if you really don't like your Friday lab and would like to do the Wednesday lab, there is space there, and it would be a little easier on the TA to balance it out. Because you had like 4 on Wednesday and now 9. And the ideal is supposed to be around 7 to 8 tops. So if you are on Friday and would like to do Wednesday, I strongly encourage and recommend that at least a couple of you try switching, and we can accommodate that.
Do we need to do it officially, like go and register for Friday lab?
I don't think so. And also, Spencer, I think you're right. Actually, we start at 10:45, don't we? So I'm getting a little ahead of myself, sorry. But this is more just talking and feedback. We're not doing any class stuff just yet. So we'll just review if anybody else comes in. You're right. I keep thinking we start at 10:35 and not 10:45. So.
Yeah, I love actually start the lecture early. So in case we have some individual questions that we don't feel bad to waste everybody else's time, we can ask them at that time.
Okay, so yeah, I've started recording and there'll be a giant 5-minute padding of us going through questions before we all officially start. So I'll make sure at 10:45 to ask any other follow-up for people who came in on time. It's not being early. In fact, I think the lab this morning technically ends at like 10:30, right? It goes from 7:30 to 10:30. So there's probably at least a couple of folks who are probably detoxing right now, taking a break before we begin the lecture. So that's a good point. So I'll answer personal questions before I get into too much detail on the labs. I keep getting ahead of myself and thinking this class is 10 minutes before it actually is.
I think it's great. It's great that we have 10 minutes extra time.
So yeah, just any personal questions or feedback for now. Yeah, 7:30 to 10:30 is the Friday labs. So it sounds like we'll get some trickling in over the next few minutes as everybody kind of wraps that up. Yeah, there's only 12 of us here, so we'll have at least a couple more showing up in the next couple of minutes.
Professor, what time was the Wednesday lab happening?
Wednesday, I think, is like 3:05 to 6:05.
3:05 to 6:05.
Yes.
Oh, okay. All right. I have a power lab scheduled for that time, but the power class is not holding labs at the time, so.
Oh, is that Arne Stolp's class?
That is, yes.
Oh yeah, he's struggling a bit to get his online stuff going. I had to go into campus yesterday and help him with the lab camera to set up. So he might be doing some remote stuff soon for some of his labs, but I know he's getting a rocky start there. But yeah, if you're able to switch to Wednesday, that would be great because it's a little lopsided towards the Friday right now.
From what I remember, I took it a long time ago, but when I was taking it, we only had lab once in a while. We did not have like the power lab every single week. So I felt like maybe when you're not having labs, you can hop in, and I don't know. Yeah, it's up to you.
Yeah, kind of tentatively, I can show up to the Wednesday lab in the afternoon, but that's kind of dependent on what Arne decides his lab is going to do.
So who watched the lectures? Hopefully everybody.
I'm pretty ready.
So some fun facts is I remember learning about Smith charts. I had this conversation with Steve Blair, how like we all learn about Smith charts for the first time, and it's just this giant, here, let me grab one here. This giant overwhelming mess of gobbledygook. And hold on, I didn't even have it right side up. And like nobody really explains Smith charts very well because there's just so much stuff on it. Like what are all these circles representing? So my goal with that lecture is just walk you through the concept of a Smith chart. And just, I want you to feel in your bones what this thing is doing. Because like, it took me years of trial and error before I really grasped what the heck this thing is all about and what the circles even represent. And even like while I'm making the lecture, I'm realizing, oh, that's what that, thing is doing. That's why they call it that. So you notice I took away all of the gunk and just said, here is the circle and here's what it kind of represents. And here's what all the little circles inside are sort of trying to do. So I really strongly encourage you to watch that lecture because compared to what the textbook does, it's just sort of like, oh yeah, Smith charts are totally cool. Let's just do something. The explanation is kind of in this. So I am hoping, my fingers crossed, if I did a good job, that Smith charts can slightly demystified.
Yeah, talking about Smith chart, I love the video you made. It explained everything really well. I'm just wondering, will you post lecture slides of that video?
Oh, right. I did slides. So let me make a note here. Post slides.
So I can print it out, so, that's something I can read just by having a handout instead of going back to the video. I don't know if that is okay.
No, that is totally okay. In fact, we still got another minute. I'm just going to do that right now while we are waiting for that last minute. Because I always forget. Most of the lectures are just kind of me scribbling on paper. So when I have actual slides, I should actually upload the slide. So I'm going to do that real fast.
So in your lecture video about the Smith chart, I do dissent on one point in which you stated that the Smith chart was invented to be a graphical representation of what it is. I argue that the Smith chart was invented to be a mechanical computer for solving linked linear equations on the complex plane.
That is probably totally valid as well.
Yeah, because in your lecture you said, oh, you could just pop this into MATLAB and it will happily solve these equations for you. Yeah. But in the 1900s, people were using slide rulers to calculate those nasty equations. So Dr. Smith invented this tool.
Yeah.
So you wouldn't have to use a slide ruler and slug it through those equations.
That is a perfectly valid and probably correct argument. And I'd say it's kind of both. Like originally, you're like, right, it's more of an analog computer. Just the numbers are there so that you don't have to crunch stuff into MATLAB. But when you actually pop out the Nano VNA, where the heck is it? Actually, look at it. It has the Smith chart option. You're obviously not like actually reading numbers off of some of this stuff per se. So we look really close. You see how it's a very crude Smith chart on there. And it's not really that you're supposed to do computations, but just sort of have some intuition from where the dots are on the chart to what they kind of represent in terms of a transmission line. So I think you're right that it is kind of more like an analog computer in a sense, just a lot of pre-computed numbers. Which I kind of have mixed feelings about because we have computers now. So why do we care about this goofy piece of paper that does complex computations for us when we can just let MATLAB do all the heavy lifting? And then the real answer, or the answer to that is, well, there's still some value in having this sort of visualization of your transmission line in terms of this sort of graphical representation. So for that reason, I'm going to really not have you do a lot of like Smith chart calculations because they feel very redundant. Like, like if I just say, here's a Smith chart and I'm going to just plot, a reflection coefficient here and say, tell me the normalized impedance, yada, yada. Like you can do that, but does anyone really do that in real life anymore when you can just plug in the equations into MATLAB and it'll do all the complex arithmetic for you? So my emphasis is really going to be more on the visualization of just, if I have a point here and I add some length of transmission line, it'll rotate around, say. Or if I have a point here at one frequency and I increase frequency down a line, will it move that way and that way? Or if I have a load and I'm moving and I add some inductance or reactance to it, how will that move around this circle? So that is how I'm going to really emphasize, because yeah, you're right. The analog computation stuff of this is really dated, I think. I would be very surprised if there's anyone with access to MATLAB who relies on a compass and rulers to actually get information off of this thing. But I think, yeah, that's kind of what it originally was, and that's a very sort of dated application for it now, because we have computers. Everybody's got MATLAB, and you can just write script to crunch the math. And so I'm not going to have you like read off the Smith chart and say, here's a reflection, now tell me the standing wave ratio using a pencil and ruler. Like I don't feel there's that much value in that, as opposed to just here is a situation now, how will it change and wiggle around? So you'll notice that's what I did in your homework problem, was stuff like, here is a 100 ohm load with an inductor, and now plot it over this little range of values. So you'll see the little arcs following the circles and that kind of stuff. And that will have some value, because eventually we're going to do like the impedance matching stuff and filters and whatnot. And that will have like little tracing around the Smith chart type effects. So that was my goal, is to really keep it conceptual and visual and not deal with the fact that it's a glorified calculator.
So we're not gonna have to call out
in support,
What'd you say?
in support, a lot of vendors do show the input impedances for amplifiers and antennas in their products. So when you're selecting an antenna or an amplifier, it's displayed in polar coordinates like a Smith chart. So there's still great value in learning it.
Yeah, and it sounds like you're saying, though, as more of just a visual intuition of the device rather than actually doing the computations and reading the values on it. So that is how I'm going to try and emphasize a lot of the Smith chart stuff. I will not ask you to do any actual hand calculations with it, because it's just equations, it's complex arithmetic, and MATLAB is more than happy to do all that heavy lifting for you. So it's 10:50, everyone is here. So some feedback on the labs. It sounds like they went relatively smoothly, just a few little rocky bumps and confusions, but overall, it seems you're pretty confident you can get that stuff done and turned in. So next week, I'm guessing there will be kind of an optional session if you want to go to it, but if you're already done and just want to use that time to write your report, that is the way it's set up. So 1 3-hour session to do the lab, 1 3-hour session to kind of write it up, and then it will be due before, the minute before you come into your next session. So with that said, there was a survey about like in-person versus remote that I'm kind of wanting to talk about, because I think, let me pull up the results. If I remember, we can look at it right now. I don't want to misremember anything. So here are the survey statistics. And I'm going to just go ahead and share my screen. Okay, so you can see we had 4 people who genuinely prefer an in-person lab, and there were 9 who prefer remote, and we have 3 don't care. So the rule was like, we need at least about 7-ish to make it worthwhile to do an in-person lab. So the only way this can work is if those 3 don't cares, if somebody wants to twist their arm or volunteer to go to the in-person, then that would be the first step. The next step on that is we have to pick a day. So I know a lot of you have fixed schedules. So even if you would prefer an in-person, we would have to pick a day, and some people may have to jump their schedules into that day. And some people may not be flexible with that, and I can't twist your arm into changing your schedule if it's already been pre-planned since before the semester. So it looks like there's a couple of don't cares. Yeah, it's kind of a nice split between Wednesday and Friday there, and with a little bit of flexibility. And then finally, the question was if we do, or sorry, yeah, would you prefer, and then are you flexible? So it looks like half of you are flexible, half of you are not, and the other half, sorry, about a third, 6, 6, and 4. Some of you are not even sure. So that would be the extra challenge on the end is, can we get enough people to do it? So at the moment, we're kind of not quite at the border to make it really worthwhile unless these 3 people here are willing to jump into a in-person class, and everyone who goes in person can pick a day that meets everybody's schedule. That's the tricky bit. So if you're really hell-bent on it and want to petition for it, then now's your chance.
I have a question.
Yeah.
What if those people go up and they do an in-person, and somebody that doesn't want in-person is forced to switch days, but they can't switch lab days because they already have a class at that other time?
Right, and I can't twist your arm in that, which would mean we can't necessarily change all our plans up, because half the idea of, when you enroll in a class the week before the semester starts, you're fixing your schedule. So I can't like force you or ask you. I mean, I can ask very nicely, but if you just can't, then we won't do that. Does that make sense?
Yes.
I can't force you to do that. And I don't want to, because that just would be hard.
Isn't there a date where the University of Utah is everything's going to be online and no in-person instruction is going to happen?
Yes, that is somewhere around the fall breakish time, mid-October. There's going to be like this 2 or 3 week block where everything has to be online anyway. So that was a big motivator, just to be online from the start, because they're going to kind of just twist our arms and make us do that. So that's something to think about as well.
So even if we thread this needle, it's going to snap to all online later down the line anyways.
It's temporary though. It will be all online for like a 2 or 3 week block, and then they'll go back to normal again. And then I think sometime around finals is when they go all online again. It's a little weird. So I'm kind of strongly biased towards keeping things online unless there is a very clear, overwhelming demand for an in-person lab. And that was why I tried to have the quiz or the survey before the semester started, but I just didn't get enough responses to warrant any changes. So it's not off the table, but those are the things we'd have to thread around in order to make that work. So I apologize to you if you really wanted to do an in-person, but we can't without just a clear demand of enough students. But hopefully you're still okay doing the remote labs. Even if you would prefer an in-person, I hope you at least can tolerate the remote labs anyway. So we can talk more about that later, or you can send me some emails back and forth in private, or talk with your fellow students on that. But that's kind of where that stands at the moment. As far as the kits go, Mel, I was just there yesterday. Mel has about 9-ish of them ready to go as of yesterday. So he said if you want to go there in person and pick up your kit, now is your chance. He just may not quite have them all just yet. I think there's another batch that will be arriving by next week sometime to bring us all the way to our 15 or 16 kits. But if you have the option and you want to contact Mel and say, I'd like to stop by and pick up my kit, now's your chance. Go ahead and do that. There's a bunch of them that are ready to go. So go ahead and get on that. So another question was, how many students, can you just sort of type in the chat window for me? Are you enrolled in the Wednesday session or the Friday session? So I was asking this earlier, but not everyone has done, had arrived yet. Because it looks like there's a huge lopside of everybody in Friday. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 Fridays and like 4 Wednesdays or something like that. So if you are in a Friday and would like to do Wednesday, you can do that, because there's only like 4-ish, 5-ish in the Wednesday session, and then there's 9 or 10 in the Friday. And that's a little lopsided. So anybody who is willing and would like to go from Friday to Wednesday, you are more than welcome to do that. And I encourage it because we'd like to balance it a little bit so the TA isn't swamped one day and bored the next. All right. And you don't necessarily have to like petition to switch your session or anything. You can just show up at it. Just don't all of you do it at once. So I guess I would say, of those of you who are in the Friday, how many of you would like to go to Wednesday and help balance it out? The big advantage, you don't have to get up at 7 a.m. because it's at 3 p.m. So I got 1, 2, 3. Okay, you two are the first 3. That will probably balance it out. That'll bring us from like 4 to 7, maybe one more if you want to go. So I got Yashi, Ben, Sona, and Nathan. Okay, you guys are now more than welcome to go to Wednesday. And I think that'll be perfect. There'll be about 8 on the Wednesday and 6 to 8 on the Friday. And yeah, that'll be perfect. So just go ahead and put that in your schedules right now. It's all online, so it's completely flexible. All right, with that being said, are there any questions about Smith charts? Otherwise, I was just gonna kind of start doodling some of the intuition from the lecture. Because like I was saying, I really want to focus on visually what does the Smith chart sort of mean in a sort of just raw geometric sense, and how do those pictures on the Smith chart translate into transmission line behaviors. So if there are no questions, no issues, we'll just go ahead and start talking about that. So I'm gonna go ahead and pin my notes here. There it goes.
Mario, will we get a chance to go through the problem quiz thing?
Oh, do you mean the quiz we did earlier, last Wednesday?
Yes. Did you go through all of them, or?
So there's the quiz and or are you talking about the problem set for the homework?
Sorry, problem assignment. That is due on Monday.
Oh, that's kind of what we're going to start here. I'm going to do a little bit of overview of the Smith chart here, and then
Okay,
we'll talk about some of the problems.
Mhm.
So let's maybe draw a circle here. I just want to really reinforce some of the basic intuition of what is a Smith chart, and it's just a polar plot of the reflection coefficient. So you notice at the end of the day, it's just a circle. You look at the Smith chart, it's got all this gobbledygook in it, but it is a circle with radius 1. So for any passive device, you imagine a transmission line like so. So there's a Z naught. Okay, and there is a Z sub L. I'm gonna draw that like so. So this little circle here, or this little physical system with a transmission line exciting a load, there's a wave striking it, and then there's a reflection, and that gives rise to a reflection coefficient, and we're going to plot it on the complex plane. So we'll do this like so. So real and imaginary. I'm just going to pick a point here, say it is somewhere there. Okay, that is the Smith chart in a nutshell. Everything else is just bells and whistles and analog computation. So at the end of the day, I really want to emphasize this notion of thinking about a transmission line here with all those horribly gobbledygooky mathematical equations, but they have patterns to them and rules which manifest as geometric manifestations, I guess, in this plot here. So I really like this idea of taking out all of the nonsense from the chart itself and just focusing on the plot, because that is what you'll get, say, when you open up your Nano VNA, and you can barely faintly see it's got the little Smith chart. So it'll do a logarithmic magnitude over frequency, and it'll also plot, you know, all your measurements on an actual Smith chart. But you notice all the information is removed, and you just kind of have a circle with some lines in it. And that, I think, is a very valuable way to think about transmission lines at the end of the day. So remember something simple like I have the input impedance looking down a transmission line, and I'm some length L away. And we had that transmission line impedance equation. So it was Zn equals, I think it was Z naught And if I remember correctly, I think it was ZL plus JZ naught. Oops, sorry, that's a Z. Tangent of beta L, and then you had a Z naught plus JZL. I'm doing this entirely from memory, so please let me know if I got that wrong. You notice this is like a horribly nasty equation. Like it's just ugly to look at it. It's a nice closed form thing. MATLAB will do its thing, but it is a horribly nasty equation. But if you think about it just in terms of the reflection coefficient, you know, a wave will go down, it'll accumulate some phase, beta L, and then it reflects back again and accumulates another beta L. So all that happens is you would say gamma of L is gamma of 0 e to the j2 beta L, and it's a negative there. So this is a much more intuitive expression than this. So this is the value in thinking of terms of Smith charts. And there's a geometric relation where that little phase shift just means this little dot here is rotated clockwise like that. So that is the theme I really want to emphasize is, yes, here is the math. And you know, you can crunch on this by hand and write script that do that, or you have this visual intuition of what it will do to your circuit at the end of the day. So with that in mind, let's kind of walk through some of the practice questions, right? I'm going to pop up our problem set here. So the first bunch of problems, let's see, let's go back here from the beginning. So the first bit was a lot of simple stuff about calculating a reflection coefficient and how that intuitively relates to all of the amplitudes and phases. So we talked a little, we did like the first third of the problems on Wednesday. And then we talked a little bit about here's a reflection coefficient, and then we did it backwards. So yeah, given the reflection coefficient, find the load. So there's some basic algebra there. So I'm just looking for the bits about, here we are, Z in, write a MATLAB script. There we go. So I'm going to kind of skip ahead to question 14. So let's draw a little boundary here. So this is the sort of thing I will be stressing a little bit more next week, and I very, very likely will ask this sort of thing on our exam as well. But you have, it says, write a MATLAB script that plots the imaginary component of Z in as a function of distance away from the load. Use the range of L, export, okay, so we're given, sorry, where did that go? I skipped ahead. So you had something like the following. Sorry, I got ahead of myself. So I'm looking at question 10. I did a very simple thought experiment. So there's sort of two ways to think about a simple transmission line problem. So we started with, this is an antenna, and it had a load impedance of 75 plus J10. And for the sake of our example, I'm going to use different numbers, like 100 plus J25. So I'm going to put in these numbers as we go through, so that you'll have to follow along a bit. You can't just copy the solution at the end. Okay, and then we had Z naught equals 50 ohms, like so. And we're exciting it with some frequency. So I'm going to put in 1.5 gigahertz. The actual question is 2 gigahertz. The velocity of propagation, VP, is 2/3 of C naught. This is actually very common to see 2/3 of the speed of light. In particular, this cable right here has exactly that. It's about 2/3 C. So that's a very common real world value that you'll see a lot. And so then it just starts asking you a bunch of things. Calculate things like L prime. So this was our quiz question before. It was, I believe it was Z naught over the velocity of propagation. Right? Does that sound correct? And you have to calculate L prime, and it goes through. So I want to skip a little bit because it asks you to calculate this guy. But then the final question was doing a plot. Yeah, so this is what I want to get to. It was plot Z in as a function of L. So you imagine this distance L here. So the idea is you can think about this system strictly in terms of impedance, and it's pretty nasty. And you'll see when you do the plot, you get some yucky results. So I'm going to walk through this because we got some time. Because after that, we start thinking about things in terms of the Smith chart instead. So let's go ahead and do a little script here. So I just got to open up MATLAB real quick. And open up a new little test script here. Courses, here we go. There we go. I'm going to go ahead and clear my variable, or sorry, share my screen here. Okay, so in fact, we don't really need a script. We can just do this in a command window, like so. So a lot of this should be pretty straightforward. You say something like Z0 equals 50, ZL, I put in 100 plus J times 25. So you notice I like to say 1J. That will always ensure that that's an imaginary number. So you notice if I say J, it says the square root of -1. Or just 1 plus I. So I and J in MATLAB are interchangeable. You can also say 1J or 1I. You notice it did exactly the same thing. But you'll notice also if I say something like J equals 10, now I've reassigned that reserved variable in MATLAB. But if I say 1J, it will still treat it as imaginary unit. So as a general rule, whenever I play with imaginary numbers, I kind of like to always explicitly write the 1J like that. You notice you can actually say 2J and it'll multiply it by 2. So that is if you accidentally overwrite your I's and your J's, this will protect that kind of notation of being a complex number. So F is 1.5E9. And then we had an L, a length. And we're just a linear space from 0 to 0.2 and do like 1,000 samples. So that was what it asked us to do. L was from 0 to 20 centimeters, according to the homework problem here. Let me double check that. Yeah. So you're familiar with the linspace command? You could have also said something like L equals 0:001:0.2, and it would do something similar, right? So I'm more of a fan of the linspace command, though. I think it's a little more explicit. And that'll just create a linearly spaced array from the min to the max with that many samples in between. So then we just gotta calculate our, oh, right, so now we need our beta L. That thing. So I don't know what beta is yet. And beta is actually a reserved function in MATLAB, so be careful with that. I'm gonna overwrite that. So it's 2 times pi over lambda, but I don't know what lambda is. So what is my lambda? Well, lambda is C equals F. It's my velocity of propagation divided by frequency. I don't know what my, so I'm just sort of doing like this little tunnel down the rabbit hole. The velocity of propagation was 2 times 3e8 over 3. So 2/3 the speed of light. I'm rounding a bit. The correct speed of light is like 2.998, but for most situations, you can round it up a smidge, at least for something like this. There was some trouble in some of my answers before because that little rounding error would kind of throw it off, but I'm pretty sure that won't be a problem anymore. I'm doing the answers with a precision rather than a range. So in any case, there's the velocity of propagation. So lambda was VP over F, and then beta is 2 pi over that. Or you could also just say 2 pi times F divided by VP. That will also give you the exact same value. So my beta times L, you notice I like to use a capital L whenever I'm in MATLAB. Little L looks way too much like a 1, and I've had horrible bugs in my code that were impossible to track down because of that little indistinguishable distinction. So I never, ever, ever use little L's when I can avoid it. But there's my beta times L, like that. So I'm going to just say BL equals beta times L. And then you just plug this into your equation. So you get Z naught times, you have this horrible numerator thing. So I believe, let's do a little double check. I wrote it down from memory, but I'm going to pull it out of the book real fast. There we are. If you pull up my other window, you should be able to see this. There it is. Yeah, it's L plus Z naught. Yep, okay, I did have it correct. 1J times Z naught times tangent of beta L divided by Z naught plus 1J times Z L times tangent of BL. There we go. So I got a whole bunch of numbers for that. So you notice, okay, all this is nice and dandy, just plugging in equations into MATLAB. And this is what I meant earlier about how MATLAB is just more than happy to just take those equations and do all the heavy lifting for you. But this is just symbol pushing. There's not a whole lot of intuition. So a very important thing to do from time to time is pull your head out of the map and plot things to associate a picture of some kind with what all of this gobbledygook is about. So I'm going to say figure 1. So I'm opening up a figure. Now we're just going to plot. I believe it was L. I'm going to multiply it by 100, so it's centimeters. And the real of Zn, like that. And this is what you'll see, this kind of repeating factor here. I'm also going to hold on and plot the imaginary. We're going to make it red. So this is very similar to what you should see in your, when you do this yourself. The picture will look different because the values were a little different frequency and some different impedance values. But you should see something like this. You notice it's repeating because I have multiple wavelengths worth of transmission line here. And so the x-axis here is distance, that distance away from the load. So you have a load, a fixed load with some transmission line length. And as I move away from the load, my apparent input impedance does this weird wobbly thing. And so you notice this is the real part kind of going up and down, and the imaginary is cycling all over the place. And that's cool and all, but there's like no intuition in that at all. It's just kind of there. It's the impedances, they're just wibbledy-wobbling, and so what? So that's kind of the goal of that first bunch of questions. You go through all of those calculations, you do this plot, and it does a thing, but it's really kind of like, what does that mean? Where is the pattern in all of this chaos here? So to me, this is why the transmission line, or a lot of this makes a lot more sense to think about in terms of a Smith chart, because the patterns suddenly make a lot more intuitive sense there. But that was basically problems, what is that, 10 through 14? Okay, so now we're going to do kind of the same idea. So it says, imagine a transmission line, characteristic 500 megahertz with a fixed inductance and some resistance, yada, yada, yada. Oh, I should have had you plot gamma on this. So let's do that real quick. So gamma is equal to Zn. So we're not going to do question 15 yet. I'm just going to add a little bit of fun to question 14. I thought about having you do this, but then I wasn't sure about the plot. So now I'm going to do gamma. And we're going to do figure 2 now. We're going to plot the real part of gamma as a function of the imaginary, or sorry, the imaginary, like that. There we go. So axis equal. So I want to show you these two things side by side here. Oop, I accidentally closed my first figure. So I'm going to go back and redraw this. There we go. So do you all see those graphs? I'm getting a little squirrely as I focus on these things. So these are two pictures of the exact same sort of system in action. Here is the input impedance going all wibbledy-wobbledy, and then here's the reflection coefficient just twirling around a circle. And so that's the Smith chart equivalent here to this input impedance. So this is why the Smith chart is kind of nice, is the geometries are much more straightforward and intuitive than if you think about it too much in terms of impedance land. So this is interesting and important to grasp what impedance is all about, but trying to visualize any of the patterns and all that chaos is difficult. So when you think about it in terms of just what is the reflection coefficient doing in this system, I just had a load and I'm moving away from it, and it just twirls around in a circle. And in fact, if we added loss to the system, we imagine the transmission line dissipating some energy, you would get this spiral that slowly just falls into the center of the circle, right? That would be because you just have attenuation going down and back, which would manifest as your reflection coefficient approaching the origin. So just kind of burn this image into your mind of there are multiple ways to look at the exact same problem, and there's a real like geometric pattern to it, and that if you think of it in the right terms, you get a very simple pattern versus some horribly gobbledygooky thing. So that to me is, I think, the academic value in still reinforcing some of this Smith chart, the way of thinking in terms of the Smith chart. So I don't actually have you plot the reflection coefficient. In retrospect, that would have been a good little exercise to throw on top of that. But I just had you do the input impedance. So for question 15 now, we're going to do some Smith chart stuff. So I'm going to go ahead and clear everything. So it says, now we're going to do question 15. And I'm thinking of doing some more stuff like this next week, because this is very important to emphasize some of these ideas, especially if I want to make some test questions out of it. So imagine a transmission line characteristic impedance, Z naught is 50. It is excited by 500 megahertz. I'm going to just change the value a smidge and call it 750 megahertz, because why not? Terminated with a load. The load consists of a series combination between a fixed inductance, L equals 10, so I'm going to just make it 5, and some variable resistance, R. So I don't know what R is yet. I'm just going to leave it there. So it just says, write a MATLAB script that plots the complex reflection coefficient as a function of real resistance R, spanning the range of 0 to 1,000 ohms. So R is in space 0, 1,000. I'm just going to do, I don't know, 10,001 samples. Why not? There we go. The number of samples is kind of arbitrary. As long as it has a nice, smooth, continuous curve, then that's fine. Obviously, you don't want to put 10 trillion, or else MATLAB will run out of memory trying to compute it. But you don't want to do like 7 either, or you'll get a very choppy graph. So usually anything between 1,000 and 10,000 is perfect. So there we go. So the question was just plot gamma as a function of R. That is our goal. So how do we do that? So step 1, calculate ZL, okay? So we know that ZL is parallel, or sorry, it said series, never mind. Series combination of L and R. So what you can think in your mind, that's basically ZL plus ZR, right? So ZR is R for a real resistor. ZL of an inductor is 2, that's actually 1J times 2 times pi times F times L. Okay, that is the impedance across an inductor with some frequency. So then so load, I usually use L for load, but I did it for inductance. So let me clarify my nomenclature here, because usually Z load would be Z real plus X. Yeah, X is the word for reactance. So let me try this again. So XL, my reactance is 1J times 2 times pi times f times L. So now my load impedance is going to be my real plus my reactance. Oops. XL. There we go. Sorry, just clarifying my nomenclature. Otherwise, you get to confuse inductance L with load L, and it gets a little tricky. So that is a load reactance defined by the inductance there. So then gamma is our usual equation, ZL minus Z naught divided by ZL plus Z naught, like so. And now we're just going to plot real of gamma, imaginary of gamma. Now, before I hit enter, what do you expect to see? Based on the lecture, which you of course all watched, what would you expect to see when I hit enter? And the answer is there'll be a sort of a circle of some kind happening. But where will the circle be? So I have a fixed reactive bit, but I'm varying the real resistance. So if I hold up a Smith chart, I'm trying to.
The upper half?
What'd you say?
The upper half of the Smith chart?
Upper half. Okay, that's a good start. So hold on. I'm gonna go ahead and hit plot. Oh, I messed something up. It's on the other chart here. Where's my gamma? It's giving me a bunch of nans or something. Oh, I did a bad thing. Let me fix my code here. I did something wrong. So ZR was what? Yeah. Is that giving me a bunch of values? Yeah. So then gamma. Is that a bunch of, oh, that is giving me, oh, sorry, there's my problem. Dot. There we go. I didn't use my dot for that, so now I'm going to plot again. Okay, now I've got the plot in front of me. So the first thing you said was it'll be in the upper half of the plane. And the answer is yes, because an inductor has a positive reactance for all frequencies. So it is going to be in the top half plane of the Smith chart here. Any other sort of ideas coming out? Or I'm going to also do this, -1, 1, -1, 1. So now it's to scale. Another thing I ask you to do is to draw a circle around it so that sort of acts like your outside circle. So it helps to say, hold on, and I'm going to define some theta like the following, 0, 2. Then what you'll also do is plot cosine of theta, sine of theta. That will draw a circle around your plot to represent the outer border of your Smith chart. So first things first, when R is 0, I have nothing but a imaginary impedance. So the question then is it going to start at the left and move to the right, or is it going to start at the right and move to the left on my Smith chart? What do you think?
So it's like a short circuit, right?
Yeah. So R of 1 is 0, so that is no real resistance, but there will be some reactance there. So ZL of 1 has some real reactance. Oops. So there's no real, but there is reactance. So the reflection coefficient is going to change in some way. So let's think about this maybe in terms of, change my view here. So you should, if you go back to my desktop video, so here's a Smith chart. So remember, over here on the right side, this is open circuit, and over here on the left is short circuit, and the middle is matched. So this would imply R equals 0, and this is R equals infinity. So as R goes from small to big, you'll notice it will imply it goes from left to right. So we're going to be, we've established we'll be in the top half of the plane, and we're going to go from left to right. Any other fun little predictions you want to make before I present the picture? All right, we'll just go ahead and cut to the chase here. So this is what you see. Something like, and you notice it is simply one of the reactive circles here. Let me do this, axis equal. So it's forces that, there we go. So those are some useful commands. The axis equal forces it to have a nice even aspect ratio. So the red circle here is the outer border of the Smith chart. And when R is 0, it would initially be here as a short circuit, but when you add a reactance, it wants to come up here to the top half of the plane. Then as R goes from 0 to infinity, it follows one of these circles here down towards the right point. So if R were to go all the way to infinity, it would end up terminating right here on the right half. And so you see, if you zoom out in your mind, this would be a circle. So it's a little chunk of a circle there that we're looking at. All right. So that's some of the fun little intuition, because you can use this to do impedance matching, like when you do stub matching, or when you have some complex load and you just start adding a capacitor in parallel with things. You can think about it in terms of traveling along the Smith chart along these circles and this trek to try and push your reflection coefficient down to 0. So we can also play, so notice we went from 0 to 1,000. What if I go from 0 to 1,000,000, right? So ZL then became R plus XL, and then gamma did this thing. So we're going to clear, hold on, plot that again. There we go. Whoop. So this is what happens when you don't have a very continuous range of samples. So it went from 0 to 1,000,000, but it skipped some values in between because it sort of compresses things. You see how it's now getting really close to that far right term there. So for that sort of thing, another helpful command, instead of doing lin space, you can say log space, but then it wants factors of 10 and that sort of thing. So you can just cram in a few extra digits of precision. But that's the idea. So you notice there's a nice physical picture for your Smith chart when you fix your inductance and I increase my real resistance. And so similar things happen if I do this with capacitance. So if you don't mind hanging out for a minute, we'll do the exact same exercise with a capacitor instead of the inductor. But this is what your answer should kind of look like when you do that problem, just with different values. So let's do a capacitance. So in the problem it says 50 picofarad, I'm going to make it 25, just for kicks. So XL is going to be 1 over J times 2 times 5 times F times C. So that is my reactance. And so then, of course, let's change this back. It's going to look a little ugly if we go out to a gazillion like that. I'm going to do 10,000 with 10,000 points. So ZL is going to be R plus XL. And calculate my gamma, like so. And don't forget that period. That just messed me up during my lecture. That little dot divide there will give you weird results if you miss that. So we're going to plot real of gamma, comma, imaginary of gamma. And we're going to fix our axes. So hold on, axis equal. We're going to zoom out a little bit, set the borders, and then we're going to draw a circle around everything. So that. So you notice I do the same thing with a capacitor, and we're in the bottom half of the plane because a capacitor has negative reactance when you put it in series with a resistor. So it did a very, very similar thing. It started here on the left as my resistor is growing from 0 to infinity, and it's tracing out an arc on one of those circles. Okay, so any questions about that? And all we're trying to do is take that idea of signals bouncing off a load and think about that in terms of these plots along the Smith chart, because they follow very intuitive geometric patterns there. And so that is my goal, is I'm going to remove a lot of the tedium of doing the pencil and paper calculations with a Smith chart and try and think about it more in terms of what are the geometric properties of this stuff. Okay, so that's pretty much all the time we have today. That is essentially your last question on this homework. I'm going to do a little bit more of this next week. You still need to talk about like generator mismatches. We're going to do a little bit of bounce diagrams, a little bit of like dispersion and loss discussions. But really, I want to kind of emphasize this sort of stuff because I think this is where a lot of the real practical merit will be. So keep that in mind. So if you have questions, now's your chance. Otherwise, thanks for joining, and I will see you all next Wednesday. Have a good 4-day weekend.